Welcome to the debate. Look up at the night sky tonight, and, when we stare into that vast expanse, our brains tend to process it as this profound, immovable stillness. We sort of project a sense of peace onto the cosmos.
Right, it feels completely static.
Exactly. But the reality of our solar system is actually much closer to, well, a chaotic, high-speed cosmic billiard table. And Earth is just sitting there, a bright blue target, moving at 67,000 miles an hour, essentially just waiting for the next break.
And the table is incredibly crowded, too. I mean, we are constantly moving through a dense swarm of near-Earth objects, or NEOs, traveling at frankly terrifying velocities. Most people don't realize that a mountain-sized rock can cross our orbit at 15 miles per second.
Completely silently.
Completely silently. So it really isn't a question of if a massive object will cross our path and threaten human civilization. It is strictly a question of when.
Which brings us to a critical inflection point for our species. The international scientific and defense communities, from NASA to the European Space Agency all the way to the U.S. Naval War College, they've been intensely studying planetary defense. But a deep, fundamental fracture has emerged over exactly how we should protect Earth.
A massive fracture.
Yeah. On one side, there is the perspective I hold. I argue that humanity must rely on cautious, internationally cooperative, soft deflection methods. I'm talking about kinetic impactors and gravity tractors.
The slow and steady approach?
Right, because these are highly controlled, non-destructive methods. They respect decades of international space treaties and, crucially, they actively prevent the weaponization of the cosmos.
And I approach this from the perspective of pure technological pragmatism. I mean, I understand the desire for cautious diplomacy, I really do, but the physics of celestial mechanics, they simply do not care about our treaties or our terrestrial bureaucracy.
But those treaties exist for a reason.
They do, but I argue that soft methods are mathematically insufficient for the largest threats or the shortest timelines. If we want to actually ensure the survival of our species, we must develop and be ready to deploy high-yield nuclear interceptions in space. We cannot let terrestrial geopolitical anxieties stop us from building the only tool powerful enough to save the planet.
Well, let's get right into why the precision approach isn't just safer geopolitically, but is actually a proven scientific reality. We no longer have to guess if non-nuclear deflection works in the real world.
You're bringing up DART.
I am. In 2022, NASA's DART mission completely validated the kinetic impactor concept. We crashed a spacecraft, roughly the size of a vending machine, into the asteroid moonlet Dimorphos.
Which was a brilliant piece of engineering, I'll admit.
It was incredible, and we shortened its orbit by 33 minutes. We successfully altered the physical mechanics of the solar system without detonating a single weapon.
DART was a success, yes. But we have to be brutally honest about what DART actually was. It was a tiny nudge on a very small rock. And we had decades of advance warning to pull it off.
But the principle holds up?
I worry deeply that DART creates a false sense of security for the public, though. If we are looking at a larger, comet-like body, say an asteroid the size of Bennu, which is about half a kilometer wide, the math of kinetic impactors just falls apart entirely.
Because of the mass difference?
Exactly. You can't just scale up a battering ram when the target weighs tens of millions of tons. Computer models show that to deflect an object the size of Bennu, it would take roughly 87 DART-sized kinetic impactors hitting it simultaneously.
Wait, 87? But we wouldn't use 87 separate launches for a single target.
We would have to. And that is exactly the problem. Launching 87 heavy-lift rockets in a perfectly coordinated cosmic strike is physically impossible with our current terrestrial launch infrastructure.
Well, the logistics would be immense, sure.
Think about the bottlenecks. The Kennedy Space Center, Vandenberg, the European spaceports, they simply cannot prep, fuel, and launch 87 heavy payloads within the narrow orbital alignment window required to intercept a deep space object. The sheer physics demand an entirely different tool, and that tool is a 1 megaton nuclear standoff explosion.
I see why you think that, but let me give you a different perspective on the timeline and logistics issue. Because the effectiveness of any deflection strategy, whether it's your nuclear option or my kinetic impactor, hinges entirely on early detection. We have to talk about our observational blind spots.
Ah, right. Because you're assuming we'll know about the threat in time to even mount a nuclear launch?
Exactly.
Chelyabinsk is the perfect example of that blind spot.
Yes, February 15th, 2013, a 20-meter asteroid exploded over the Ural Mountains in Russia. It released energy equivalent to about 440 to 500 kilotons of TNT.
Which is massive.
To put that in perspective, that is roughly 30 times the destructive power of the bomb dropped on Hiroshima. It blew out windows across 200 square miles, injured 1,500 people, and the most chilling part of that entire event?
We didn't see it coming.
It was completely undetected until the moment it hit the upper atmosphere.
Because it approached from the direction of the sun. Ground-based visible light telescopes are completely blinded by the solar glare. It's what astronomers refer to as approaching at a high phase angle.
Basically looking directly into a searchlight to try and spot them off.
Exactly. It is a fundamental architectural weakness in our current planetary defense system. Even with the new space-based infrared telescopes we are planning to put at the L1 Lagrange point.
Actually, let's clarify what the L1 point is for the audience, because that's really crucial to the detection argument.
Right, of course. The L1 Lagrange point is a stable gravitational parking spot about 1 million miles away from Earth, directly toward the sun. It allows a telescope like NASA's planned NEO-Surveyor or the ESA's NEOMA to look continuously at the space around Earth without being blinded by our own atmosphere or the day-night cycle.
It's the ultimate vantage point.
It is. But here is the terrifying math. Even with a state-of-the-art thermal infrared telescope parked at L1, looking into those high phase angles, our maximum warning time for a Chelyabinsk-sized object coming from the sun side might only be 5 to 12 days.
And that 5 to 12-day window brings me exactly to my point about infrastructure. I look at our investment in these next-generation space telescopes as building a cosmic smoke detector. Okay, if we deploy the NEO Surveyor and ground-based assets like the VRC Rubin Observatory, we are going to find the vast majority of these major objects decades in advance. If we have the smoke detector and it gives us decades of warning, why do we need to keep a nuclear sledgehammer on the nightstand?
I worry profoundly about what I call the readiness paradox.
The readiness paradox? Explain how that applies here.
Well, to use a nuclear standoff weapon effectively, particularly for the short warning events you're so concerned about, you can't build it from scratch when the rock is spotted.
No, obviously not. You'd need it assembled. You have to maintain a ready-to-launch nuclear arsenal specifically mated to deep space launch vehicles. You have to keep it fueled, armed, and ready on a launch pad or in a silo 24/7 for decades.
Right.
The readiness paradox dictates that maintaining a live, network-connected nuclear missile aimed at the sky for 50 years is statistically more dangerous to Earth through accidental launch, miscalculation, or, a catastrophic cybersecurity breach than the statistical probability of a major asteroid impact. We are introducing an immediate, guaranteed existential risk just to mitigate a theoretical one.
I understand the anxiety around maintaining that kind of hardware. And I agree, the cybersecurity of command and control is a massive hurdle. But your analogy of the smoke detector assumes the fire will always start as a slow, smoldering ember that gives us time to calmly fetch a bucket of water.
Usually with celestial mechanics, it does.
But what if the fire is an explosion? What if a long-period comet drops into the inner solar system from the Oort cloud, orthogonal to the plane of the ecliptic?
Meaning it drops straight down on us from above the solar system rather than traveling along the flat disk where the planets orbit.
Exactly. It completely bypasses our usual scanning planes. In that scenario, we wouldn't have decades. Best case scenario, orbital mechanics might give us 22 months from detection to impact. And as I mentioned before, 5 to 12 days for a sun-side approach. In those windows, your preferred slow methods like the gravity tractor are utterly useless.
Well, let's look at the gravity tractor, because I think it's misunderstood. It requires almost no mass and is highly controllable. You take a spacecraft weighing just 1,000 kilograms, and you park it about 155 meters away from the asteroid.
Just hovering there.
You don't touch the rock, you just hover. Using mutual gravitational attraction, the mass of the spacecraft gently pulls the asteroid. Consuming a mere 1.4 kilograms of chemical fuel a month, you impart a microscopic velocity change. Over a few years, it is enough to steer an asteroid away from a gravitational keyhole, a region in space that would otherwise lock the asteroid into a future Earth impact.
But a velocity change of microns per second is entirely useless if the asteroid is already on a direct terminal collision course and we only have 2 years to react.
But even if we magically get your 2 years of warning, your nuclear sledgehammer assumes the asteroid is a solid rock. This brings us to a massive physical problem. You're treating asteroids like they're solid pool balls.
Well, some of them do have immense structural integrity. Iron-nickel meteorites are incredibly dense.
Some do, yes. But modern planetary science missions like OSIRIS-REx at Bennu and DART at Dimorphos have proven that a vast number of these objects are what we call rubble piles.
Right, basically floating gravel pits.
Exactly. They are not solid rock. They are highly heterogeneous, loosely bound collections of boulders, gravel, and dust held together by incredibly weak microgravity. If you hit a rubble pile with a massive, localized force, like a heavy kinetic impact, or worse, a nuclear blast, you risk unintentionally disrupting the entire body.
You're talking about the fragmentation risk.
Precisely. You crack the egg, you turn a single predictable bullet into a radioactive shotgun blast. Instead of one localized impact in an ocean, you get a dozen massive impacts across multiple continents. The probability of Earth suffering a devastating multi-city extinction event actually increases if you shatter the object poorly.
That assumes a disorganized fragmentation, though.
Which is why the precision of a gravity tractor or a very calculated mild kinetic impact is so vital. A gravity tractor doesn't care about the composition of the asteroid. It treats the rubble pile as a single center of mass and gently tows it without ever risking a fracture.
I'm sorry, but I just don't buy that. Let me tell you why. You are fundamentally mischaracterizing how a nuclear standoff explosion actually works in the vacuum of space. We are not burying a warhead inside the rubble pile to blow it apart like a firecracker inside a dirt clod.
But the sheer energy transfer of a megaton device.
The energy transfer is entirely focused on the surface layer through a process called radiation coupling. A standoff burst is specifically detonated at a calculated, optimal distance away from the asteroid, maybe a few hundred meters. In a vacuum, there is no blast wave of air.
Right, no atmosphere to carry the shockwave.
Instead, the nuclear device releases an immense flood of X-rays and neutrons. Those X-rays hit the surface of the asteroid and instantly flash boil the top millimeter of rock. That vaporized rock expands rapidly into space as a superheated plasma. It acts exactly like a massive rocket engine strapped to the side of the asteroid. Newton's third law kicks in, and the thrust of that escaping plasma pushes the entire massive body uniformly in the opposite direction.
But modeling that uniform push requires a precise understanding of radiation transport and the material properties of the asteroid at extreme pressures.
We have decades of hydrodynamics data from underground nuclear testing. We know exactly how high-energy X-rays interact at silicates and carbonaceous materials. And in the absolute worst-case scenario, where the warning time is so short that we actually have to intentionally disrupt the asteroid, say we only have 3 months, a close proximity nuclear burst is powerful enough to robustly disperse the fragments.
By blowing it to pieces?
By shattering the body and pushing the debris cloud so violently that the vast majority of your so-called shotgun blast is swept out of the Earth's path entirely.
I don't dispute the raw physics of X-ray ablation. If we lived in a perfect simulation, maybe it works every time. My deepest concern, and this is where I think the pragmatic engineering view develops a severe blind spot, is the geopolitical and legal quagmire we actually operate within.
Ah, right.
We don't launch rockets in a vacuum. We launch them from a politically fractured Earth.
And here is where we usually get bogged down in terrestrial politics instead of focusing on planetary survival.
Because the politics are inseparable from the technology. You can't just ignore human nature. Look at the U.S. Naval War College analysis. Impulsive techniques, specifically deploying nuclear explosives in space, blatantly violate the spirit and the strict letter of foundational international laws.
You mean the treaties from the 60s?
Article 4 of the 1967 Outer Space Treaty expressly forbids placing nuclear weapons in orbit or on celestial bodies. The Comprehensive Nuclear Test Ban Treaty forbids nuclear explosions in space.
Those are treaties written half a century ago at the height of the Cold War, long before we mapped the NEO population and fully understood the existential threat of near-Earth objects.
They were written to prevent us from annihilating ourselves. How do you differentiate between a planetary defense system and a malicious orbital weapon? You physically can't. The technology is inherently dual use.
But the intent...
If a global superpower announces they are placing a 1-megaton nuclear device on a heavy-lift rocket, claiming it's a quote-unquote planetary defense interceptor, how does the rest of the international community trust them? How do rival nations know that rocket won't achieve orbit and then suddenly be redirected toward their capital city? The very deployment of nuclear planetary defense forces a geopolitical crisis that could spark a terrestrial nuclear war before the asteroid even gets here.
Look, there's a concept in defense circles called R2DE, the responsibility to defend Earth. Basically, it means our survival as a species has to trump our terrestrial arms race anxieties. We need to legally reclassify a nuclear device used for this specific purpose.
Reclassify a nuclear bomb.
Yes. It shouldn't be classified as a weapon of mass destruction under the 67 Treaty. It must be classified as an instrument of planetary survival. Geopolitical bureaucracy is simply too slow for cosmic realities. Let's look at the timeline of building a spacecraft. Even a standard non-nuclear scientific probe takes 36 to 48 months just to navigate the design reviews, the assembly, the testing, and the launch integration.
Which is precisely why we rely on international institutions, like the International Asteroid Warning Network, or IAWN, and the Space Mission Planning Advisory Group. They exist to coordinate these efforts ahead of time, transparently, without violating weapons treaties.
I agree that international advisory groups are vital for tracking and observation. But when a 10-kilometer rock is detected 3 years out, an advisory group has no teeth. If the United Nations bogs down in debates over dual-use technologies, treaty violations, and mutual suspicion while an extinction-level event approaches, humanity will literally legislate itself into going the way of the dinosaurs. We will die debating the legality of our own survival.
So your solution is to advocate for unilateral action? Just break international law and hope the other nuclear powers don't retaliate?
My solution is to build trust through action. History proves we can actually do this. Look at the Apollo-Soyuz test project in 1975.
The joint space flight.
Exactly. At the absolute height of the Cold War, the United States and the Soviet Union, two nations actively aiming thousands of nuclear weapons at each other, managed to dock their spacecraft in orbit and shake hands. Scientists and aerospace engineers are remarkably capable of creating what we call free space.
Free space.
Yes, zones of pure technical cooperation that sit above political barriers. If you give the international engineering community the mandate to build a joint, fully transparent, internationally monitored nuclear defense platform, they will build it. We cannot let the fear of what we might do to each other stop us from preventing what the universe will do to us.
It's a beautiful historical example, but have you fully considered the modern cyber landscape? A joint internationally monitored nuclear platform requires a level of continuous digital integration that makes it highly vulnerable.
There are risks, sure.
The command and control structures for a shared nuclear asset in space, accessible by multiple nations to ensure transparency, would be a cybersecurity nightmare. A bad actor wouldn't need to build a rocket. They just need to hack the network. I still maintain that expanding our observational infrastructure is the only sustainable, non-apocalyptic path.
Observation is crucial, I agree.
Right. If we fund the Vera C. Rubin Observatory properly, if we ensure the NEO surveyor launches on time and gets to L1, we essentially buy ourselves the most valuable resource in planetary defense: time. With enough time, we never need the nuclear option. We can rely on highly controllable, non-destructive kinetic impactors and gravity tractors.
I am 100% in favor of observation. We need NEO surveyor at L1 yesterday. But physics dictates that we will eventually find an object where time is not a luxury we possess. A comet from the Oort cloud will not care about the Vera Rubin Observatory. High-impulse nuclear options are the ultimate necessary safeguard against the massive or the sudden.
It seems we are looking at two entirely different sets of risk tolerances. I view the introduction of live nuclear weapons to the space domain as an immediate, high-probability risk to human civilization through accident, theft, or war.
And I view the lack of a nuclear planetary defense as an unacceptable vulnerability to a low-probability, high-consequence cosmic event.
I think that captures the divide perfectly. But there is a near-term event that I think we both agree is going to force humanity to mature its approach to this entire problem, and it's happening very soon.
You're talking about the arrival of Apophis?
Yes. On Friday, April 13th, 2029, the asteroid Apophis, which is roughly 340 meters across, basically the size of the Empire State Building, is going to fly past Earth.
And it's not just a distant flyby. It is going to come closer to Earth than our geostationary weather and communication satellites.
It will literally skim the edge of our orbital infrastructure. It will be visible to the naked eye for millions of people across Europe and Africa. It is a once-in-a-millennium close approach for an object of that sheer size. And critically, we know for a mathematical fact it is a peaceful encounter.
Right, it's not going to hit us.
But as a scientific opportunity, it is totally unprecedented. It allows us to observe how Earth's tidal gravitational forces might alter the asteroid's rotation or trigger surface landslides on a rubble pile in real time.
Exactly. And combined with the data we will get from the European Space Agency's Hera mission, which arrives at Dimorphos in late 2026 to perform the ultimate crash scene investigation of our DART impact, we are entering a golden age of asteroid mechanics.
We'll finally see the crater.
Yes! Hera is going to map the exact crater DART left behind, measure the precise mass of Dimorphos, and finally give us the hard data on how much momentum enhancement we actually got from the rubble pile ejecta spraying into space.
Those two events, the Apophis close approach and the Hera rendezvous, represent incredible opportunities. They are chances for humanity to refine our impact models, test our tracking networks, and practice exactly the kind of international scientific cooperation I am advocating for, all done with shared data, full transparency, and zero nuclear weapons required.
For now. But the hard data from Hera will also tell us exactly what the physical limits of kinetic impactors are. I suspect it might just prove my point about how much raw force is truly required when we inevitably face the larger threats.
Well, we will have to let the data speak for itself when it arrives. It is a profound, almost philosophical challenge, trying to align our fragile, mistrustful human political frameworks with the unyielding physical mechanics of the solar system. For those listening who want to see exactly how this incredibly complex puzzle is unfolding in real time, I highly recommend looking deeper into the ADA collaboration, the Asteroid Impact and Deflection Assessment.
It's some of the most fascinating applied physics happening today, and it represents our best minds working on our ultimate survival.
It truly does. We started this discussion by looking up at the night sky, imagining a peaceful canopy that is, in reality, a cosmic billiard table. The break is coming. Whether we meet it with a delicate, precise nudge or a massive, pragmatic shockwave, the fact that we are finally looking up, tracking the table, and preparing might be humanity's greatest collective achievement.